In this video, I'll go over the development of Runge-Kutta methods for differential equations. After studying this video, you should be able to explain how higher-order Runge-Kutta methods can be formulated using the Taylor series. Recognize how Hume's method and the midpoint method are examples of the more general class of second-order Runge-Kutta methods, and understand conceptually the classical fourth-order Runge-Kutta formulation. So let's talk about developing higher order methods from the Taylor series. So if you recall, Euler's method was basically developed taking the first two terms of the Taylor series. That's how we got Euler. So the most natural idea to take a higher order method would be to take the first three terms. So this presents a problem though, because now we need to figure out how to deal with the second derivative term. So one approach could be to use a finite difference formula for the second derivative. So here's a finite difference formula, if you recall from that list of finite difference formulas. A second order accurate, and we'd want that for a higher order method, a second order accurate finite difference formula for the second derivative. And we can plug this back in and use that to develop an algorithm that is second order accurate. However, we have a problem. Recall the way that we would do that is we would then solve, and we'd have everything in terms of dy dt, which is our ODE function. So we could develop a method that way, but the problem that we get is we bring in another point. And that I minus 1 point that we'd have to bring in makes things more difficult to implement. And also less computationally efficient. So the Runge-Kutta approach can achieve the accuracy of using this higher order Taylor series without requiring that calculation of a higher derivative. And what that does is it allows us to still use a one-step method. And recall our general formulation for the one-step method is we're using everything from yi plus 1 and yi and just using an increment function to move forward one time step h. So let's look at the Runge-Kutta formulation. So again, this is a one-step method, and what we're going to do is evaluate that increment function as a linear combination of evaluations of the function dy dt that defines our differential equation. So we'd have some constant times k1, where k1 is the dy dt function evaluated at the ith time step. And then we have another constant a2 times k2, where k2 is dy dt evaluated at time step ti plus p1h, and so p1 is going to be a constant that tells us how far along the time step we're going to take some intermediate time value between I and I plus 1, defined by p1. And then q11 is another constant, and k1 is our function evaluation from the previous term, k1, and on into n terms, and this would be for an nth order Runge-Kutta method. And so we keep moving down. Notice as we move down to k3 for a third order method, we just keep adding more constants, p2, q21, and q22. And so all of these constants, we're just going to use the Taylor series to determine them for some desired accuracy. And let's see how we do that in the context of a second order Runge-Kutta method. So we'll again start by solving an initial value problem, dy dt equals f of ty. And for a second order Runge-Kutta method, we're going to use a linear combination of two function evaluations. So we have a1 k1 plus a2 k2, all of that times h. So this is our increment function again for our one-step method. And just like on the previous slide, k1 is going to be the function that defines the ODE evaluated at the ith time step. And k2 is going to be the function evaluated at some intermediate time determined by that constant p1, gets us somewhere in between ti and ti plus 1, and it could be at ti plus 1. And yi is incremented again using k1 to increment yi. So we substitute k1 and k2 into the increment function. We can get everything together for our second order Runge-Kutta. And what we need to do in order to formulate this algorithm is we need to solve for a1, a2, p1, and q11. So we need to find those four constants. And as I said on the previous slide, the place we're going to find them is from the Taylor series. So since we're doing a second order method, let's compare. We're going to compare this Runge-Kutta approximation for yi plus 1 with the second order Taylor series expansion for yi plus 1. So that's again going to be yi plus dy dt evaluated at ti times h plus 1 over 2 factorial times the second derivative of y times h squared plus terms order h cubed and higher. And so to find our constants, we're just going to make sure that these two approximations, second order approximations of yi plus 1 are equivalent. So let's look at how we do that. So let's start with the Taylor series. So here's our Taylor series, and what we want to first recognize, so what I've done here is plugged in for our dy dt. Let's go back here for a second. So this term right here is f of t and y, evaluated at the ith time step, because that is how our ordinary differential equation is defined. And then the second derivative term we can write as f prime at ti and yi. So we'll plug those in, and let's move forward from there. So we'll plug those in. So here's f at ti and yi, and f prime at ti and yi. So we've just plugged those into the Taylor series. And then if you recall from calculus, we can use the chain rule to find the total derivative of f. And so that total derivative of f, or f prime of ti yi, is equal to df dt plus df dy, the partial of f with respect to y, times the partial of y with respect to t, all evaluated at ti and yi. So I'm going to go ahead and plug that in to our yi plus 1. So we get yi plus 1, still working on our Taylor series approximation, is yi plus f at ti yi times h plus 1/2, and now we're going to plug in that total derivative, df dt plus df dy times dy dt, and all of that times h squared plus terms order h cubed and higher. We're going to call that equation 1. And now we're going to go back to the Runge-Kutta approximation for yi plus 1. So looking back at our Runge-Kutta approximation, what we're going to do is focus in on the K2 function evaluation. So this K2 function evaluation right here, and we're going to work on that term. And we'll start with a Taylor series expansion. So here's a Taylor series expansion of the function evaluation K2. And if you recall way back earlier in the quarter when we looked at nonlinear systems, we talked about the Taylor series expansion of a function of two variables using partial derivatives. So we're incrementing t by the quantity p1h, and we're incrementing y by the quantity q11 k1h. So our Taylor series expansion is going to be p1 f of t I yi plus p1h times the partial derivative df by dt plus q11 k1h times the partial derivative df dy plus terms order h squared and higher. And you may wonder, why aren't we keeping that second order term, since we're deriving a second order method? And that'll become clear in a second. So we'll plug this Taylor series expansion here for K2 into our K2 term. So remember, we had A1 K1 plus A2 K2, and now we've approximated K2 with the Taylor series expansion for K2, and you'll see that when this order h squared air term, when that multiplies by this h here, that's where we'll get an order h cubed term. So let's look at multiplying that out. And so what we get is yi plus 1 is equal to yi plus, we're going to multiply through that h, a1h times f of ti yi plus a2h times f of ti yi plus a2 times p1 times h squared times df by dt, and move down here now, plus a2 times q11 times h squared times f valued at ti yi times df by dy plus terms order h cubed and higher. Next, we'll collect like terms. And when we collect like terms, we see not a whole lot to simplify here, but we do have this term and this term are the same. And so we get yi plus 1 is equal to yi plus a1 plus a2 times f at ti yi times h plus a2 times p1 times h squared times df dt plus a2 times q11 times h squared times f at ti yi times df dy plus terms order h cubed and higher. And let's call that equation 2. And what we're going to do is compare equation 2 to equation 1. So if we look back here, let's look at the first term. So we have yi. Looking back at equation 1, we have yi. Then for the second term, we have a1 plus a2 times f of ti yi times h, and here we have just f of ti times yi times h. So that tells us that those two constants, a1 plus a2, they have to sum to 1. If we look at our next term, we have here 1/2 df dt times h squared. Well, let's look over here. Here's our df dt term. So df dt times h squared. So this tells us that a2 times p1, that term right there, has to equal 1/2. Now we can look at our df dy term. And coming back here, we have df dy times dy dt times h squared. But recall dy dt is f of t I yi. So that's just like the other term, and again we see it's 1 times df dy times f times h squared. So again, a2 times q11 times h squared times f times df dy. So a2 times q11 also has to equal 1/2. So that gives us now 3 equations for our 4 unknowns. We have a1 plus a2 is equal to 1. We have a2 times p1 is equal to 1/2. And a2 times q11 is equal to 1/2 for our second order Runge-Kutta. And it turns out what we need to do is just choose. And typically what we do is we'll choose a value of a2 because we have 3 equations for 4 unknowns. We need to choose something. And choosing a value of a2, that gives us our version of second order Runge-Kutta. So if we choose, for example, a2 equal to 1/2, then a1 is going to equal 1/2, and p1 and q11 are both equal to 1. So we can look at plugging those in to our Runge-Kutta formulation, and we get yi plus 1 is equal to yi plus, plugging in for a1, which is 1/2, 1/2 k1 is f at ti yi plus 1/2 and a2, so a2 is 1/2, and then k2 is now going to be f at ti, and p1 is h, so ti plus h, and yi plus q11 is 1, k1 is f at ti yi times h. All of this times h. And what you see is this is that Euler method predictor, and what we've really shown here is we have 1/2 of the slope at TIYI plus 1/2 of the slope at step I plus 1 times h. So this is an average of the two slopes, or this is actually Hume's method without a corrector iteration. Another typical formulation is to take a2 equal to 1, which makes a1 equal 0. p1 and q11 are then equal to 1/2. So we would get yi plus 1 is equal to yi plus a1 equals 0. So we have no k1 term. And then a2 is equal to 1. And then k2 is going to be f evaluated at ti plus p1 is 1/2, so 1/2 h, and yi plus 1/2 is q11 times k1, which is f at ti yi times h. and all of that times h. And what we see here is here's Euler for a h over 2 step, and here's our h over 2 step. So now we've used Euler to predict the slope at the h over predict yi at the h over 2 step, yi plus a half, and then using that slope estimate at 1/2 of the time step as our increment function to get to yi plus 1. And that again is the midpoint method. The last common version is to take A2 is equal to 2/3, A1 is equal to 1/3, which results in P1 and Q11 are equal to 3/4. And this is called Ralston's method. It doesn't simplify much to plug those in, and so it doesn't really tell us anything new, so I'm not going to do that. But where Ralston's method is significant is it's actually, you can show with an analysis that gives us the minimum truncation error. So all of these are second order accurate, so they have second order truncation errors, but Ralston's method gives us the minimum. So that's how we would derive a second order Runge-Kutta. Commonly used is a fourth order Runge-Kutta method, and the most common form for the classical fourth order Runge-Kutta method is yi plus 1 is equal to yi plus 1/6 of the quantity k1 plus 2k2 plus 2k3 plus k4 all times h. This is derived in a similar way to what we just did, but I'm not going to take you through that. It's quite a bit longer to get to the fourth order term, to get to the fourth order accurate truncation error. But you should recognize a lot of these different function evaluations. So if we imagine conceptually what's happening here is we're going to start at ti, and k1 we're basically going to use like a midpoint method to get k2. And then looking at k3, k3 is actually going to use that k2 result, that result of that midpoint, to do another midpoint slope estimate at I plus 1/2, and then using the k3 result, getting all the way to k4 to I plus 1, we'll use that k3 slope to predict I plus 1 and get that fourth estimate. And this is kind of like going and getting the corrector for Hune, analogous to Hune. And then we're going to take a weighted average of all three. So 1/6 of k1, 2/6 or 1/3 of k2, 2/6 or 1/3 of k3, and 1/6 of k4. So what's happening is this method is derived using the Taylor series, analogous to how we did the second order Runge-Kutta derivation. But conceptually, what we're doing is taking a number of slope estimates in between I and I plus 1, 4 slope estimates, using similar methods to what we've looked at, midpoint and Hune, and using a weighted average of those slope estimates to get our increment function, P. Sorry, that actually includes the 1/6. So that concludes this discussion of Runge-Kutta, and we'll look at applying it in MATLAB in the next video.